Hello everyone, this is a continuation of section 9.2 on vectors, and we're going to continue to move through the notes here. We're talking about magnitude, which is the length of the vector, and I've already mentioned it a few times in terms of what it is, but this is our calculation for it. So the length of the two-dimensional vector is here, and the three-dimensional vector is here, and it's a very easy calculation. All you're going to do is take the square root and then you're going to square each of the components and add them up. Now, I did mention this in section 9.1, but with magnitude, I will often or almost always write it with two bars. Our textbook, the Stewart textbook that we use, does only one bar, and some schools, some colleges and universities use one bar, some use two. So you have to be aware of that, depending on where you maybe go off to school and whether or not you are going to take some math there. So you want to be able to read it either way. But just keep in mind that some of our notes will have that single bar in there. But often what I do is I write it as the double bar. If you are to have a position vector, like let's say that the position vector is right here, and we'll call that A, and so this would represent A sub 1, and this length here would represent A sub 2. So this is our position vector. So the vector is A sub 1, comma A sub 2. The magnitude is simply just the distance formula of a position vector. That's really all it is. It's just the run, the A sub 1, the horizontal, and then the A sub 2, the rise. So that's really what the distance formula, or the length of vector is the distance formula that we had studied in section 9.1. But if you have that position vector where the origin is the initial point, that sort of simplifies down the whole process. You can see where that comes from. Okay, to add vectors algebraically is very simple. We're just going to add their components. So if you have A sub 1 and A sub 2, and you're going to add that to B sub 1 and B sub 2, all you're going to do to get your resultant vector is add A sub 1 plus B sub 1 and A sub 2 plus B sub 2. And that's it for adding. Very simple. To multiply by a scalar, also really, really simple. If you have, let's say, 3 multiplied by the vector A sub 1, A sub 2, you simply just multiply each of the components by 3. So it'd be 3A sub 1 and then 3A sub 2. All right, let's do example 4 and sort of just put a number of these things together that we've been studying. So we have our vector A and we have our vector B, and we're going to first find the magnitude of A. So the magnitude of A will be the square root of, so we're going to take 4 and we're going to square it, and 0 and we're going to square it, and 3 and we're going to square it. So that gives us the square root of, let's see, that's going to be 25 because it'll be 16 and 9, and so our magnitude is 5. And then next what we're going to do is find the sum of the vectors. So we're going to do A plus B. And again, we're just going to simply take the components of A and add them to the components of B. So we're going to take 4 and we're going to add it to negative 2. So we have for our first component 2. And then we're going to take 0 and add it to 1, so we get 1. And then 3 and add it to 5, and we get 8. So that's going to be our sum A plus B. Then we're going to do A, and we're going to subtract B. Now remember, technically this is A plus negative 1 multiplied by B. That's really what it is mathematically. And so what we would have then for A is 4, 0, 3. And for B, we would be multiplying it by negative 1. So what we have, if we were to sort of break down every element of this, is A plus negative B, which is going to be 2, negative 1, and negative 5. All right, and then if we add these up, what we get is the vector 6, negative 1, and negative 2. All right, then we're going to find 3b. So we're going to take our vector b and we're going to simply multiply the components by 3. So we get -6, and 3, and 15. Okay, then the next one, sorry, the last one is 2a plus 5b. So we have 2a plus 5b, and that gives us, I'm going to write it all out so that I don't lose you. I think you all are hopefully doing well with this, but I want to make sure it all makes sense, especially for those of you that vectors are a little bit new, although a lot of this is just simply algebra. But we have 8, 0, and 6, and we have -10, and 5, and 25. And so then our answer to this last one will be -2, -2, and 5, and then 31. So I hope that makes sense. With example 4, it just kind of puts all of that stuff together. And then again, just as a reminder, you want to make sure that even the easiest stuff you just dig into and make sure you understand, so that as we build onto the more complex stuff, you're okay with that as well. Below this, you can see that there are a number of properties of vectors. We're going to go through these off and on as we continue to study this topic. We've already talked a little bit about this, the commutative property where we're able to add a plus b or b plus a and they become the same. One of the things that I will talk about soon, I've already mentioned it a little bit, but it's the zero vector. And so the zero vector would, through addition, not cause anything to change. That'd be the identity, and so on. You can kind of look through those. All right, let's move on to the next page. Okay, so here we are going to talk about the unit vectors. And if you've studied vectors at all, which I know some of you have, the unit vectors are very common. You have I, j, and k. If you are working in 2 dimensions, then obviously k would be disregarded because you don't need to deal with that. You're just dealing with I and j. On a grid, what these are going to look like is right along the x-axis, you will have your vector I. So your vector I is, and I'm just dealing with right now, let me write this out. So this is 3 dimensions, and then 2 dimensions, you'd have I equal to 1, 0, and j equal to 0, 1. So if you're looking at a plane, the xy plane, I would simply be the vector that goes 1 unit out along the x-axis and 0 units in the y direction. And then j would be 0 units in the x direction and 1 unit in the y direction. So that's your vector, your unit vectors I and j. If you're in space, let's see if I can draw this to make it look all right. So we have, let's do x and y and z. And so our unit vector I would be here, and our unit vector j would be here, and then our unit vector k would be there. And so the unit vectors I, j, and k are just utilized in our study so that we're able to rename things if needed, or reorganize things if needed, or better reference in which direction we're looking at these things. And so right now, all we're talking about is just the notational pieces to this. This is not really getting into the why of this yet. But for instance, if you had a vector A that was made up of a sub 1, a sub 2, a sub 3, you could write it as it is written in the problem right here, or you could also write it as a sub 1 multiplied by vector I plus a sub 2 multiplied by vector j plus a sub 3 multiplied by vector k. And that's just a different way of writing it. I hardly ever do this unless I have to, just because it's more writing. So really, I mean, if a question like example 5 says, okay, please do this and write it in terms of I, j, and k, well then, okay, I guess we can do that and get our credit. But again, it's just something that I typically use the other notation just because it saves me a little bit of time. So anyway, that's what it would look like if you were to use the unit vectors. Okay, in example 6, we have a and b, and we're going to express the scalar multiplication of each of those and the addition of them in terms of I, j, and k. So what we have then is 2 multiplied by I, 2j, and -3k. And then we're going to add 3 times 4i plus 7 k. Now, in this case for b, obviously j is not represented in the notation there, and so if you were to write it in the first notation that we had practiced, it would look like this, where there would be a 0 there. That's the only part that can get a little bit goofy, because if we gloss over that and kind of read too quickly, we might think that it's 4i and 7j, and that maybe k doesn't. So we just have to be kind of careful with little things. I tend to make those mistakes. Um, so to finish the problem, we would have 2i plus 4j minus 6k plus 12i plus 21k. And then we'll just add up the different components here. So we get 14i plus 4j plus 15k. And that's going to be your final answer there. All right, the next piece to our notes is the unit vector. And we're going to use the unit vector a lot in our area of study here for multivariable calculus. Unit vector is simply just a vector that has the same direction as whatever original vector we were analyzing, except it's 1 unit in length. So again, if you're looking at a vector that is maybe we're concerned only with the direction of the vector, we're not too concerned with the magnitude, we might make it a unit vector in order to analyze the direction, but not really be too concerned about how long the vector is. We'll do this a lot, even especially later in the year when we're looking at chapter 13 and we're looking at vector fields, or we're looking at fluid flow or something like that. We're not really concerned necessarily with how long a vector is. We're maybe more concerned with the direction that it's moving, or if it was a fluid flow or a particle that's moving. So the calculation for this is really easy. All you're going to do is you're going to take your vector u, and it's going to be equal to whatever the vector you're analyzing is, divided by the magnitude of that particular vector. So in other words, what this is a scalar. So we're actually scaling vector A by 1 divided by that vector's magnitude. So we're making a unit through just a simple multiplication. Let's go to the next page and I'll show you the example of this. All right, so in example 7, we're going to find the unit vector that has the same direction as the particular vector that we're given. So let's just call this vector v, and this particular, or you know what, I'll back up and call it a, and that's what we were using with our formula on the previous page. So let's say that vector a is 2, -1, -2. The first step is that we're going to find the magnitude of this vector a, and the magnitude is simply just the square root of 2 squared plus -1 squared plus -2 squared, and that gives us a magnitude of 3, because we'll get the square root of 9. That's going to be our magnitude of the vector we're analyzing. Then what we're going to do is we're going to calculate the unit vector by taking that magnitude 1/3 and multiplying it by vector A. And so we get a unit vector 2/3, -1/3, and -2/3, which is the exact same direction as the original, but 1 unit in length. Here's another example. Same kind of thing. We're going to find a unit vector. I'm going to pause the video and I'll write it out. You can try it on your own. All right, so here's my work for example 8. Again, at any point when you're watching these videos, you can certainly pause and try a problem and then come back to the video and take a look at what I've written. That might be a helpful way for you to not only study a little bit, but also try some of these on your own. All right, let's take a look at example 9, just a little bit of a twist on what we're studying here. So we have a vector that is the same direction as -2, 4, 2, but it has a length of 6. So one of the easiest ways we could do this, let's first label this as vector v. So one of the easiest ways we could do this is we could first find the magnitude of v, which is going to be the square root of -2 squared plus 4 squared plus 2 squared. And that's going to give us the square root of, let's see, 24. And that's the same as 2√6. So that's our magnitude currently. So let's say that we were to take that particular magnitude and multiply it by -2, 4, and 2. Well, what length would that give us as a vector? Well, that would give us a unit vector, right? So if we were to find the vector that was in the same direction as -2, 4, 2, but of length 1, that's what we just found. That's what this is. This would be length 1. However, we want length 6. So instead of multiplying it by 1 over 2 root 6 to make it a unit vector, let's multiply it by 6 times that to make it a length of 6. So our final answer here would be the first component, let's see, would be -6 over root 6. The second component, if we were to reduce it, would be 12 over root 6. And then the last component would be 6 over root 6. So that would be the same direction that we're looking for, but of length 6. Okay, in our final video for section 9.2, I will talk to you about some of the applications to vectors, which specifically we're going to look at forces. So that will be in our next video.